Okay, so let's summarize what we've discussed so far and make a summary of Gauss's law. Gauss's law says that the total electric flux through a closed surface, and this circle on the integral sign means that it's a closed surface of some shape. You can take any shape you want. And the electric flux is equal to the charge inside the surface over epsilon naught. Epsilon naught is just a constant. The flux is E, electric field dotted into area. Area has a vector nature. We've discussed this before. And remember, for a closed surface, that the area vector points from inside to outside. It has to point from inside to outside for this equation to be correct. And the electric field that we use here is the electric field due to all charges in the universe. And the Q inside means the charges only inside the surface. And intuitively you can think about this, because if you make a surface of any shape, any field line that goes through one of the surfaces will have to go through all the other surfaces. So the electric flux is the same. That's an intuitive way of thinking about it. We've proved it mathematically, and we showed that when the charge is inside the surface, that the contribution to the electric flux for an arbitrary surface doesn't depend on the shape. It just depends on the amount of charge inside divided by epsilon naught. One final point, we didn't really derive Gauss's law, and that may sound like a surprise. We derived Gauss's law for the case when the charge inside is fixed in space, it's not moving. What happens if the charge is moving? What if the charge is moving in some arbitrary way, like any kind of motion? Will Gauss's law still be valid? Yes, Gauss's law is still valid. So the proof that we've given actually is, the proof was only done for the case where the charge was at rest. But it turns out that it applies also for any kind of motion of the charges. And so this is an important point, and that's the reason why Gauss's law is very important. It's because it's one of the equations that's always correct, no matter how the charges are moving in space. So in our derivation before, we used Coulomb's law to get the electric field at the surface. But remember, Coulomb's law is only valid when you have static charges. If the charges are moving in some arbitrary way, the electric field is actually very, very complicated. So it's not Coulomb's law. You can't use kq over r squared. So that's where the problem with our derivation was. It was only limited to the case where the charges are at rest.